So this is the last chapter, chapter 18, exam 7. There's no comprehensive final. The finals week is next week. And unless they tell me different, we'll come in on Monday at the same time as always and take the chapter 7 exam. I'm going to introduce the material for chapter 7 now. And since there's no time to do a review, you'll have to look at the recording.
And that's in
Brightspace, right? The review I did, it's probably the one from last summer, but it covers the same material, the same review document. There should be no surprises. And we're going to get rolling. Let's see. I need to share. And let me share this one right here. There we go. And other things. Yes. Yes. Okay. Just in case I need it. All right. Electrochemistry is exactly what it says. It's chemistry, but we focus on movement of electrons. These terms, well, there's a proper definition for electrochemistry. The interchange of chemical and electrical energy. When I think of electrochemistry, I think batteries. But there's more to it than that, of course. But that's a good place to start. And there are terms that we need to master. Oxidation, reduction, and then oxidizing agent, reducing agent. So let's get those under our belt. There we go. The best way to remember oxidation, what oxidation is and what reduction is this acronym, oil rig. Oil stands for oxidation is loss. That means loss of electrons. So when electrons are lost from any atom, it's said to be oxidized. And reduction is gain. And by the same token, of electrons. One or more. And the other important factor to remember is anytime this one happens, that one has to happen. You can't transfer electrons into empty space. They got to go somewhere. So if something is oxidized by losing electrons, something else has to be reduced by gaining those electrons. Then we have the reducing agent and the oxidizing agent. If you have something that's oxidized, since they always occur in pairs, if this is oxidized, it's causing the reduction of the other one. So this one would be the reducing agent, causing the reduction. This one, of course, would be the species that's reduced will cause the oxidation of the other one. So it's the oxidizing agent. All right, we'll have some examples in a minute. All right, we need some rules. And these rules are established for our bookkeeping scheme so that we can keep track of where the electrons are and where they're moving. So we need to just agree upon certain oxidation states. Or oxidation numbers. The oxidation states are analogous to charges. So if you do have an ion, like a sodium ion in a reaction, then its oxidation state is going to be +1. But we have to extend that to covalent compounds also. And you don't have ions with covalence. So we need some rules that help us assess the oxidation states of some variables. So here we go. The first one is Oxidation state of a neutral atom is 0. So if you have, well, let's say you have a gold atom. That's oxidation state 0. Or if you have a diatomic, like oxygen, in its most stable state at room temperature and pressure, then the oxidation state of each oxygen atom in that molecule is 0. Okay. That's the first rule. Second rule is one we've covered already. If you have an ion identified, then its oxidation state is the charge. If it's a separate atom, a separate ion, or it could be an ion in a compound that we know is ionic, then this would be a +1, that would be a -1. Okay, based on the ionic charge. Then if you have oxygen in a covalent compound, like water, right? It's going to be taken as an oxidation state of -2. And of course, that makes hydrogen a +1 because neutral compounds must, this is one of the rules, must add up to a 0 total. The only exception to oxygen as a -2 is peroxides. If you have a peroxide, and the most recognizable peroxide is hydrogen peroxide, right? Everybody's got that in their medicine cabinet. Then both of these together, -2. So that means each one has to be a -1. So anytime you have a peroxide, the oxygen atoms, each atom is a -1. All right. I mentioned hydrogen already. Hydrogen in a covalent compound is +1. And in a covalent compound, we have to assume that hydrogen is a +1. Let's take a different one. How about methane? And that one is taken as +1. That's a covalent compound. Which means now we can calculate what carbon is, because 4 times +1 is +4. That means this carbon has to be a -4 to balance the charge, to balance the oxidation states. Now, the only exception with hydrogen is if it's in an ionic compound paired with a metal, for instance, like aluminum hydride. Right? Aluminum has to be positive, right? Because it's a fixed charge. We learned that early on. It's a +3 charge. That means hydrogen has to be a -1. So anytime you find a hydrogen paired with a metal, it's going to be -1. All right. Let's see, next, fluorine. Fluorine is always -1. No matter what compound it's in, fluorine is -1. Oxidation number. Now, it's the members of its group, the halogens, can vary. But there are times when we have to make a choice. And like I said, this is a bookkeeping scheme. I mean, it's not absolute chiseled in stone. It's a way of tracking electron movement. So when you have something else in the compound with fluorine, of course, it's -1, that's no problem. But if we have something paired with a chlorine, like phosphorus and chlorine, which one do you take as a rule? Well, phosphorus doesn't have a rule, but chlorine is the closest we have to a rule because it's a halogen. So in that case, we take chlorine as -1. And I'll show you examples where we have to do that. All right, next rule. We've already mentioned this one. The oxidation states of neutral compounds must add to 0. And then the second one is like it, the number 7. The oxidation states of polyatomic ions must add up to the charge on the polyatomic ion. So for instance, if we have nitrate, that we know that oxygen's -2. We've already established that. -2 times 3 is a -6. Okay. What oxidation state on nitrogen added together with -6 will give you a -1? Well, +5. +5 and a -1 and -6 gives you that charge. Okay. Sometimes I say it like this. All right, we've got a -6 total for oxygen, but I need to hold one of them out for that charge. So I say I got to balance a -5. That's where I get +5. That's the way my mind works. All right. And rule number 8. When you have an alkali metal in a compound or an alkaline earth, their charges are fixed. Alkaline metals are always +1, alkaline earths are always +2. And those compounds are going to be ionic. Oh, I did add this one to the list. Chlorine. When chlorine's in a compound, it is -1. Unless it's paired with some other element with a rule. Right? These rules are set up so that the one above it takes precedence. Right? So if chlorine is combined with, say, fluorine, fluorine gets the -1. And then we calculate chlorine. Nitrogen is another problem that I failed to mention. If nitrogen's in a compound with some other element that doesn't have a rule for it, then we take nitrogen as -3. And we simply do that because noble gases are 0, halogens are -1, chalcogens are -2, nitrogens are -3. And you're going to find possibilities. Right? The cyanide ion is a good example, really. Right? Which one do you choose? Well, we go for the more electronegative one, which is nitrogen. To the right of carbon would be -3. That means we hold out one of them for that charge, and that carbon is a +2 oxidation number. All right, I think that's all the rules. Yeah, now we'll do some examples. All right, potassium dichromate. Okay, this is a neutral compound. We know that alkali metals are always +1. So that means we're given a total of +2 oxidation states from that potassium. Oxygen's -2. So that's a -14 total. Right? If we add those two together, we get a -12. Okay. So now those two chromiums have to balance that -12, which means each one must be a +6. Okay. That's one way to do it. The other way to do it is we know what dichromate polyatomic ion looks like. It's like this. Okay. So now we can take -2 times 7 is -14, but we got to hold two of them out for that charge, charge. -12. This has to be balanced by +12, which each one's +6. Either way works. Okay, that's potassium dichromate. And let's see, there should be some animation here with it. Yep. How about the carbonate polyatomic? Right? Oxygen is -2 times 3 is a -6 total. Got to hold two of them out. Right? So we're only going to neutralize 4 of those negatives. That means that carbon is a +4. Okay. Manganese dioxide. We have a -2 times 4 is a -4. -2 times 2 is a -4. That means this one manganese has to be a +4. And then we have this example that I mentioned earlier. right? If we don't assume that chlorine is a -1 in this case, we're stuck. We can't do anything. So we have to say -1 times 5 is -5 total. That phosphorus is a +5 oxidation number. And then sulfur tetrafluoride. This one's easy because fluorine is given as -1, no exceptions. So that sulfur is a +4. Okay. All right. Now, the reason we've got to learn these rules and oxidation numbers is so that we can tell where the electrons are moving in a chemical reaction, or if they are moving. Some reactions don't transfer electrons as redox reactions. This introduces the idea of the half reaction. Now, this equation is balanced already, just so that we can use it to make a point. Let's see, it's 2+. And then we got manganese, 2+. Yeah, and -5 iron, 3+, plus water, 4 waters. That's a balanced oxidation reduction reaction. Notice that we've got ions everywhere, right? with no counter ions. Now, it's possible that some of this positive charge balances that negative, but not all of it. We have an imbalance in charge. What that means is there are counter ions in here that are not given. They're spectators. So they'll be the same on both sides. We leave them out for convenience because they're just kind of muddy the waters. Or we could conduct this reaction with any counter ions we want. As long as they're spectators, we can make those ions anything, like potassium or sodium or whatever. We still get the same reaction. These are the important players in the reaction, and it's balanced. Notice it has hydrogens on this side and waters on that side. That's going to come into play a little bit later when we balance an equation that is in a form that's not complete. And this would be in acidic solution because of these protons. Okay, now, the first thing you do is assess the oxidation numbers so you can find out where the electrons are moving. Right, this one's obvious. That's a +1. That's a +2. That's a +2. That's a +3. This is a -2, and this is a +1. And then this is a -2. I'm gonna put it down here so it doesn't get confused with that one, because that's the charge on the polyatomic. And what does manganese then give us? 2 times 4 is a -8. We hold one of them out. That means this is a +7. Okay. All right, now we can see which one moved where. If we look at hydrogens, there was no change. +1, +1, right? No electrons moved with hydrogen. Manganese is +7 to +2. Right? So that one did change. How did it change? How do you get from a +7 to a +2? You can only add or subtract electrons, right? You can't mess with the protons. We learned that early on. So that means you had to neutralize 5 of those with 5 electrons. And then that left 2 positives over. Okay. So that means we had to add, right? Sometimes I draw tie lines. Let me get this out of the way. Going from here to here, we had to gain 5 electrons for each manganese. Okay. gaining electrons, reduction is gain. So that means this species was reduced. And if we write the reduction step, then we're at minimum, we're going to have this manganate ion with this +7 manganese going to manganese 2+. I do better than that. There we go. And then to get there, we had to add 5 electrons. Right? So if you gain electrons, they are reactants. So that means the oxidation step would be what? Iron went from +2 to +3. That means there was a loss of 1 electron per iron, but we had 5 irons. So we actually had 5 electrons lost from this group of irons. And this is 1 manganese equals 5 electrons. Notice the same number of electrons that are gained are lost. So if we write the oxidation step, we're going to have, let's see, 5 irons at 2+ each gives us 5 irons at 3+ each plus 5 electrons. Now, what happened to the hydrogens and the waters? Well, the fact is, you don't need hydrogens or waters to balance this down here because there are no oxygens, there are no hydrogens. But you do need here. So these 8 hydrogens go here, and these 4 waters go here. Notice 8 hydrogens, 8 hydrogens. 4 oxygens, 4 oxygens. So we're not breaking any balancing equation rules. Okay, so that's what it should show you there in that slide. The reduction step is the top one, oxidation step is the bottom one. And that's how we split an equation into half reactions. These half reactions simply means that half of it is reduction, the other half is oxidation. And we're going to use that technique to balance an equation. These are the rules, right? Just they're in blue and green. And we're going to do one, so I'm just putting them up there for posterity's sake. And there's a flow chart. And the first approach we're going to make is balancing equations in acidic solutions. So that means we're going to have these hydrogen ions and waters. All right, so let's balance this one. Entirely different reaction. And we're told this reaction is oxidation reduction. Right? So we don't have to figure that out. But it's going to become obvious once we start working with it. So this is dichromate. Yeah. Cr2O7 2-. And let's see, everything's in aqueous solution, so I'm not going to write aqueous in there. And then we have this sulfide ion yields chromium 3+ and sulfate. So at this point, all we've identified are the reactants and the products in this reaction. But it's not balanced yet, obviously. All right, because we just determined that this one was +6, didn't we?
Mm-hmm.
Yeah, +6. Right. So we know that chromium is going to be reduced from +6 to +3. Then we need to do sulfur. So -2 times 3 is -6. Hold 2 out, that's a +4. And this is a -2 times 4 is -8. Hold 2 out, this is +6. So sulfur was oxidized. Let's make some room here, just pull those out. There. All right, so let's see, the oxidation step, the reduction steps. Be like that. So who was oxidized? The sulfite was oxidized to sulfate. So we're going to have this one in the oxidation step. I'm going to put that up there, just make it error proof. And +6. And the reduction step is going to have the dichromate with its +6. Yep. And the chromium 3+. Okay, now that we've got them separated into their half reactions, you start balancing them. First thing you do is you look at anything that's not oxygen or hydrogen and be sure they're balanced. We got 1 sulfur and 1 sulfur. That's good. 2 chromium, we need 2 chromium. Then you go for the oxygens. We've got 3 oxygens on this side and 4 on that side. So that means we need another oxygen over here. And we put the oxygens in as water. Okay, but now we've added 2 hydrogens. So we've got to add 2 hydrogens on this side as protons. Okay, now we got the hydrogens and the oxygens balanced. On this side, we've got 7 oxygens here. So we need 7 waters. That gives us 14 hydrogens, 14 protons. Okay. Now we're going to do the electrons. In this case, we went from +4 to +6. That means we lost 2 electrons for each sulfur. And there's only 1 sulfur, so 2 electrons total. Okay. Let's see. I'm going to keep up with the slides here. There we go. Slides. Let's get ahead of ourselves. Let's get the electrons for this one. So we went from +6 to 3+. So that's 3 electrons had to be gained for each chromium. So that means 6 electrons total had to be gained, correct? Okay. Now that we've got hydrogens, oxygens, electrons balanced for each half reaction, we've got to balance the electrons for between the 2 before we can add them back together. So since we have 6 here and we need 6 here, I think if we multiply by 3, because this half reaction now, all these reactants and products are established ratios. So anything we do to one, we have to do to all of them. That means 3 times this would give us 3 there, 3 there. That'll make 6 here, 3 there, and a 6 there. Now that we've got equal electrons, we can add them together. Right, the electrons are not going to come down because this side cancels that side. Now we have dichromate. And let's put these down here first. 14 hydrogens. Then we'll go up here. 3 water plus 3 SO3, 2 minus. That takes care of this side. And the other side, 2 chromium 3+ 7 water plus 6 hydrogen plus 3 sulfate. Go. Now we look on either side and cancel whatever we can. 14 hydrogens here, 6 hydrogens there. So if we cancel those 6, that leaves us with 8 over here. 3 waters on this side, 7 waters on that side. Cancel those 3 waters, that leaves us with 4 waters on that side. And we can't reduce it any further, right? Because that's a coefficient of 1. So let's see. Let's move along on our slides. Okay, there are the half reactions. Balance the oxygens and the hydrogens. Then we balance the electrons and add them together. So 1 dichromate, 3 sulfites, 8 hydrogens yield 2 chromium 3 plus, 3 sulfates, and 4 water. So we're balanced now. And this is the overall redox equation balanced properly. Last semester, we learned how to balance equations using my budget method. There are some redox equations that will balance easily with the budget method. You don't have to track the electrons. But for most redox equations, the half reaction method is the most reliable. Once you know that you have a redox equation, then you go for this half reaction method and you can't miss. The other thing that it will do for you is it allows you to balance the equation in either acidic solution or basic solution. We've balanced in acidic solution with these hydrogens. In order to make it basic, you go this far and then you just convert it to base, right? Add hydroxyls on both sides. Like that. This makes 8 water. And with hydroxyls on this side, then you have 4 waters over here. That makes 4 waters. So if we were to do this in basic solution, it would be dichromate plus 4 waters, right? These are gone, plus 3 sulfite, and then 2 chromium 3 plus, 8 hydroxyls, and 3 sulfates. That would be in basic solution. Now, I have to always remind my students, some of them catch it, some of them don't. When we write this equation as is, just like it is down here, if you have these hydrogen ions in the equation, they're all together. Reactants and products are in the same mix. So if we say these hydrogen ions are there in the mix, then yeah, they're accessible from both sides. Same thing with hydroxyls. If we have hydroxyls in there, this is a basic solution. They're in the solution together. The only time they're separated is when we physically separate them. And that's what we're going to do when we make a battery or a galvanic cell. But for now, everything is together, mixed in the soup. All right. Let's try this one. We do okay with time. All right, balance the following equation. So we got bromide ion. Let's see, they're all, no, bromine, there's a liquid. So I'm gonna have to put the phases in here just to keep things organized. Okay, that's going to form a bromine liquid and manganese 2 plus in an aqueous solution. Okay, so we need to separate the oxidation and reduction steps. Bromine is going from -1 to 0. So that means it had to lose an electron. Okay, that means it was the oxidized one. Bromine -2. Oops, that should be a 2. There. had to lose. And that means this one is probably the reduction step. Let's confirm it. Let's see, -8, balance -7, that's a +7 to 2 plus. Okay, so yeah, this one was reduced. We had to add 5 electrons. I'm just going to put this in there now because we're talking about it. Had to add 5 electrons to go from +7 to +2. And that's just for one manganese. Bromine had to go, actually it would balance 2 of those. So we had to lose 2 electrons, 1 electron for each one. Kind of doing them out of order, but it still works. Now we'll balance the oxygens. We don't have to balance oxygens for this one because there's none there. But we do need 4 oxygens on this side. There. And 8 hydrogens to balance that side. Okay, now we want to balance the electrons. Let's see. Let's keep up with the slide animation here. Oh, it only gave us the answer. Okay. Well, let's keep on moving. We've got 2 electrons here, 5 electrons here. So how do we balance 2 against 5? They're both prime numbers. We can't divide. If we multiply 5 by 2, we get 10. Then we'd have to multiply 2 times 5 and get 10. So that's what's called cross multiplication. So we're going to make this one a 5 factor and this one a 2 factor. That means this one is 10. This one is 5. That one's 10. This one will be 16. This one will be 10. This would be 2. This would be 8. And this one would be 2. There we go. Now, let's see, we can cancel the electrons. Right? How about, well, hydrogens and waters are the same. We're going to bring them down because there's nothing up here to cancel. All right. So let's see. Let's put them in order. 10 bromide in aqueous solution. Okay. And let's put the manganese next. Plus 2 MnO4 minus aqueous solution. Then we have 16 hydrogens. Now on this side we have 5 bromine liquid. And we have 2 Mn2 plus aqueous. And let's see, then we have 8 waters. That's it. Okay, let's see if that agrees with the slide. Let's see, 10 Br minus, 16 hydrogens, 2 MnO4 minus, 5 Br2s, 2 Mn2 plus, and 8 waters. Okay, that's acidic solution. So, in order to balance, using the half reaction method to balance equations in basic solution, I use what I call the fake acid method. You balance the acidic solution first, and then you convert all your hydrogen ions into water with hydroxyls and balance the hydroxyls on both sides. It just adds another step to the procedure. All right. The question may occur to you, and it did to me, you know, why do I go to the trouble of balancing in acidic solution just so I can convert it to basic? Why don't I just go straight to basic? Well, You'll have to add water in order to compensate for the oxygen added by hydroxyls. But water is a different ratio. When you add water, you're adding 2 hydrogens for every oxygen when you only need 1 hydrogen for every oxygen. So you're complicating the situation with an extra hydrogen that you've got to put somewhere. So you're going to have to put a hydrogen ion on the other side anyhow and neutralize it with more hydroxyls. So that just adds another step. Makes it more complex. If we do it acidic first and then go basic, then we avoid that problem. All right. What do we got here? Oh, balance the following in basic solution. Okay, we can do that. Cyanide ion. Everybody's favorite. Yeah, that is if you're a murderer. Or an organic chemist. They like cyanide ions. They're particularly reactive for certain syntheses. And MnO2, that's a solid. Okay, so we've got to separate these into oxidation and reduction steps. All right, we did this one before, but we have to assume nitrogen is -3. So that means that carbon is a +2. We did this one before, I think. -2, -8, 7, +7. And this one, we've got 2 assumptions. Well, we have a rule for oxygen, -2, but we have to assume -3 for nitrogen. That means what? A -5 total, but we need an extra negative held out for that one. So this one's a +4 for carbon. And then with a -2, -4, we've got to balance the whole thing, +4 for that main. All right, now we can decide which is which. The carbon, nitrogen, we've made nitrogen -3 on both sides, so we can't do anything with it. Oxygen didn't change. Carbon went from +2 to +4. It means it lost electrons. It's the oxidized step. +2 there, and we go to CNO minus the +4. Well, we go ahead and, well, no, let's take it in order this time. Then we got left over is MnO4 minus with +7 for that manganese. And this manganese is MnO2 +4. So that means we had to gain electrons to go that route. Okay. Carbon and nitrogens are balanced on both sides, manganese on both sides. Now we can balance oxygens. We only have 1 oxygen over there. Now we need 2 hydrogens over here. We've got 4 oxygens here and 2 there. So we need 2 more oxygens here. That gives us 4 hydrogens on this side. Now we can do electrons. All right, oxidation step. We're going to lose 2 electrons for every carbon, and there's only 1 carbon. So we lost those 2 electrons. This side, we're going to gain 3 electrons. -3 and a +7 is a +4. So we're going to gain 3 electrons. Now we need to balance the electrons. We got 2 there and a 3 here, so we're going to cross multiply. 3 there, 2 here. That gives us 6 here. 6, 3, 3, and 3. And then this makes 6. And this makes 8. That makes 2. This is 4. That's 2. That. Okay. Now let's go ahead and bring these down. The electrons are gonna cancel out, so we don't have to break those down. But we have 3 cyanide. We have 2 manganate ions. And we have 8 hydrogens here. And we have 3 waters. Let's see. 1, 2, 3, 4. 1, 2, 3, 4. On this side, we have 3 CNO minus. We have 2 NO2. Okay, those 2, then we have 4 waters. And 6 hydrogens. Okay, that's 1, 2, 3, 4. 1, 2, 3, 4. So now we've got 8 hydrogens on this side and 6 on that side. So that leaves us with 2 here. We got 3 waters here and 4 waters there. That leaves us with 1 here. Now that we've got it balanced in acidic solution, and we can't reduce it any further, right? 3, 2, 2, 3. There's nothing we can divide through by that will give us a whole number multiple. We're going to neutralize the hydrogens with hydroxyls. So that means on both sides. Okay. So these 2 give us 2 water. Okay. We'll use those up. And we got 1 water on that side. So we balance the waters, that one goes out and just leaves us with 1 water and 2 hydroxyls. So the final equation should be 3CN minus 2MnO4 minus, yep. 1 water, yes. 3CNO minus 2 MnO2s and 2 hydroxyls. That's in basic solution. Now, that's when everything's in the soup together. What we're going to do now, when electrons move, that means there's a potential for extracting energy from that movement. So when those electrons move, if everything's in the same soup, you don't have access to those electrons. Right? You can't gain anything from them. They're moving freely on their own. So what we want to do is separate these half cells, oxidation reduction cells, separate them apart and force the electrons to move externally through a circuit. That's what we're doing with the galvanic cell. That way we can tap into that electrical energy that's available in those moving electrons. Now, in order to do that, the galvanic cell, we have to set it up so that the movement of electrons is spontaneous. In other words, all we have to do is connect the cells in a circuit and the electrons move. We don't have to do anything to them, they just move. That's spontaneous. This is a point. Let's see. This is the way it would look. The way we would make it in the lab. Like if we had time to do the electrochemistry lab, we'd do this, we'd make a battery. And we have a solution over here. This would be the reduction side. This would be the oxidation side. And we would have an electrode here submerged in that solution. And we have an electrode submerged in that solution. And then we would have an external circuit that would usually have a voltmeter attached to it. Yeah. Now, nothing's going to happen this way because that's a broken circuit. Remember, in physics, in electricity, you have to have a completed circuit in order for electrons to move. That's true with a flashlight, and it's true with house current. We see power coming into the house through these lines at 240 volts, or actually it's 120 volts per line. But when you double them up, you can get 240. But one line coming in is pushing electrons into the house, right? For a complete circuit, where do they go? They go into the ground, right? When we get through using them, they go into the ground, and the producer of the electricity, the power station, they have their ground also. So the earth is part of the circuit. They force the electrons through the wires to our house. They go back through the ground, back to the power station. So we need to connect the two. When we do it in the lab, we would have done it with what we call a salt bridge. We have salt in here. I think I had potassium chloride salt. So we had potassium ions and chloride ions. And we had auger in here also. That's just to keep the solution from moving in bulk, like coming out and just transferring over. That way, only the ions can move. The other way you can do it is put a porous disc between the two. Okay, put a porous disc here. And then only the ions can move. Either way works. Okay, so on the reduction side, what's happening? Electrons are being put into the equation as a reactant. So electrons are coming out of this side right here. We've got electrons coming out here. And here, on the oxidation side, we're losing electrons. So the electrons here are moving that way. They're coming from the reaction and going into this circuit. So on this side, the point is that the reactions, the half reactions, the reduction reaction and the oxidation reaction are occurring right there at the electrode, because that's where the electrons are. And if you remove electrons here, then you leave a positive charge behind. So how do you balance that? Well, you replace them with negative chloride ions that move out of this salt bridge. And on this side, you're adding electrons to this side and building up a negative charge. So the potassiums move out on this side to balance that charge. Okay, that's a general schematic for a galvanic cell. And by convention, we put the reduction on the right and the oxidation on the left. Sometimes you'll see it the other way around, but that's standard procedure. Sometimes you have to assess it and say, all right, did they do that right? Maybe they didn't. Okay, here's another setup with either the salt bridge or the porous disc. One of the advantages of a porous disc is there's no resistance. There's almost no resistance to movement of ions. Whereas with a salt bridge, you do have some significant resistance in the movement of ions, which reduces the overall voltage of the cell. Right? It's an internal resistance, we call it, in batteries. All right. Let's see. Right. The right-hand side is oxidizing. So on the reduction side, you have an oxidizing agent that is receiving the electrons. And on the oxidation side, you have a reducing agent that is delivering electrons. And we also have another name. This side, this whole thing here is called the cathode. And the cathode is always the site of reduction. The oxidation side is the anode. And it's always the site of oxidation. That's important distinction because you can force this thing to run backwards. All you need is an external voltage that opposes the spontaneous voltage in excess so that it runs backwards. And in that case, now you've got reduction on this side and oxidation on that side when you force it to go backwards. So in that case, the cathode would be on this side. But now we're talking about batteries, spontaneous reaction. Cathode is on the right for reduction and anode is on the left for oxidation. All right. So what would be what we call the cell potential? What's the voltage here? All right. This is equal to the cell potential. Right. And if you have access to a fancy script, that's what the E is for. But since I don't, I'll usually write it this way. That would be the electrical potential, E equals something. Or we call it electromotive force. That's a good way to describe the voltage. Electromotive force. That's the force at the atomic level that is pushing those electrons. It's forcing them to go this way. Electromotive force. And it's in voltage, in volts. 1 volt is equal to the amount of work that is done for every coulomb of charge transferred. So that means it's 1 joule per coulomb. Now, coulomb is a unit of charge that we haven't discussed yet. It was developed in the 19th century in honor of one of the scientists working in that area. He was a Frenchman. Obviously, his name was Coulomb. But it's a certain charge value, and it was useful for their research to fix the value at 1 coulomb at a certain value of charge. And that's equal to a charge movement. Now, there's a conversion between coulombs and number of electrons. And we'll get to that in a few minutes. You'll need to know that. Oh, I've got a video. Okay. Let's see if it'll play.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The 2 solutions are connected by a porous sodium chloride salt bridge that prevents the 2 solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay, so notice that there was no water, no hydrogens there. There was no need. So this reaction could occur in neutral solution, acidic solution, basic solution, doesn't matter. Well, there are some engineering considerations, but from pure chemistry, it doesn't matter. But the other thing that you may notice is when the anode is operating, zinc metal ions are being converted to zinc 2+ ions. So they're leaving the surface of this electrode and decreasing its mass. And on this side, copper 2+ is being converted to copper metal and deposited on that electrode, and that mass is increasing. And you can detect that, right? Weigh the electrode before, weigh the electrode after, and see that it's either lost or gained. Oops, we'll see it again. So how do we measure cell potential? Right? We have to be able to quantify the electromotive force, the voltage of a cell. And one way is to use a voltmeter. A voltmeter is designed to measure the movement of current through a resistor. So the voltmeter is attached to one side here and one side here, and the electrons are forced, the current is forced through the voltmeter, and it has a standardized resistance in it. And they use Ohm's law to determine what the voltage is. Take myself into a corner. Let's see. V I R. So this is voltage. This is current, right, in amps. And by the way, an amp is 1 coulomb moving past a fixed point every second. So 1 amp would be that. And then resistance is measured in ohms, and we give it that symbol, the capital omega from Greek. So if you know this in your voltmeter is constant, and you can measure the current moving with your circuitry, then you can calculate the voltage, and that's the voltage that's reported in the dial. Right. The maximum voltage that's available to the cell using any method, the maximum voltage is under zero current when there's no current moving. Because if there's current moving, then you're experiencing some resistance and the voltage is going to drop. As soon as the electrons start to move, you drop below the maximum cell potential. Right. So the voltmeter is not going to give you the maximum cell potential. It'll be pretty close, but it won't be the maximum because you're introducing a resistance. So in order to actually measure the true maximum potential for a cell, you need another device called a potentiometer. What this one does is it introduces a voltage in the reverse direction. Okay, and you adjust the voltage until you get no current. So the voltage, the cell voltage equals the reverse voltage, and current is 0. That way, you're calibrated for your reverse voltage. You just flip the sign, and that's the cell voltage under 0 current. That will give you the maximum voltage for this cell. Potentiometers are more expensive though, right? So you have to buy them special. If you go to any hardware store or go to Walmart, you're going to get a voltmeter or a multimeter, right? They now combine several functions, but the voltmeter is the cheaper way of doing it. The potentiometer requires some fancy electronics and some expertise, actually, because you've got to adjust the voltage until there's no current. Then you read the voltage. Okay, that's how we measure voltage. Let's see. Most voltmeters, when you attach them to a battery or to a cell, they're very forgiving. If you attach the leads in reverse, then it'll give you a negative value. So you just need to change the sign or switch the leads. By the way, the spontaneous reaction that occurs in a galvanic cell always gives a positive voltage. If the voltage is positive, then the reaction is spontaneous and it's moving in that direction. If you get a negative voltage, then you've got it running in the wrong direction. Now, we want to be able to calculate the theoretical potential for a galvanic cell. When we combine this half reaction and that reaction, we want to know which way is it going to be spontaneous and what's the voltage? What can we expect as the maximum voltage from that galvanic cell? In order to do that, we need to know, we need to know respective voltages for each of the half reactions. Well, here's the problem. If this half reaction is not attached to another cell, you're not going to get a voltage out of it. So what we devised is a standard to which all half cells are measured. Well, first we need conditions. In order to have E0, which is standard potential, under standard conditions, that's what that zero means. That means all the solution components are at 1 molar concentration. If there are any gases involved, say your electrode has a gas being emitted rather than a metal electrode, the gas has to be at 1 atmosphere. Okay. And the temperature is generally taken as 25 degrees C, standard temperature. Now, when you look it up in a table, all the values for the half cells are given as reductions. They're standard reduction potentials. So this one, of course, would be written correctly. Right? If it were on this side of the cell, it would be copper 2 plus 2 electrons yields copper. But this one would be written zinc 2 plus 2 electrons yields zinc. And it would be given a voltage, a reduction potential. Against what? What is the standard? Right, compared to what? Compared to the standard hydrogen electrode. So if we were to do this one here, then on this side, rather than zinc, let's just change it a little bit. Right. Rather than zinc, we would have a tube going to a hydrogen source under 1 atmosphere pressure, and it would be pushing hydrogen bubbles out here. Now, this tube would also have to have a conductive surface on it, right, because a glass tube won't conduct. So usually we attach also a platinum electrode. Right, that's how the electrons move. You got to go?
Yeah, I got a review to go to, but you, just to be sure, you said the review is going to be online for the next test, right?
Yes. Yeah, you have to look at probably the summer recording.
Okay.
Should be right there. Okay. So this is our standard hydrogen electrode. And by convention, the standard hydrogen electrode over here, this is given as 0 volts. So any value we get measured here is going to be the standard potential for that half cell. All right. And there are the conditions. Table 18.1, I think, is in your textbook. It's got many of the standard reduction potentials for any half reactions that you'll encounter. So if you find a half reaction that you want to put with two half reactions you want to put together, and one of them must be an oxidation step, then you reverse the reaction and you change the sign on the reduction potential. If it's negative, you make it positive. If it's positive, you make it negative. We'll do some examples here in just a second. If the half reaction, when you combine the half reactions, as we did in our balancing equations, if you combine them and you have to multiply by an integer, the E0 does not change because E0 is an intensive property. It doesn't matter how much. And I mentioned this one earlier. When you set up a galvanic cell, the spontaneous direction, which will dictate which reaction goes on which side, which is cathode, which is anode. The arrangement of those two half reactions is the one that gives you a positive voltage. That will mean spontaneous. Right? Here's part of that table, not all of it, just part of it. Right? If I put the whole table up here, the print would be too small to see. But what you'll see is these are standard reduction potentials. All of these reactions are recorded as reductions. The electrons on the left-hand side, right? This one has the highest positive voltage against the standard reduction potential of hydrogen. Right? And then we just keep going down. And notice they get smaller and smaller as we move down. And we get to the point where now here's our standard potential right here, 0. Everything above it is positive, everything below it is negative as a reduction. Okay. And the video mentioned the reactivity of metals. In other words, which is more active than the other. And what they mean by that is which one loses electrons more, is more likely to lose electrons than the other. And you can compare those as reduction potentials. So if we say compare, let's go back up. Let's compare, let's go back up here. Okay, there's copper at 0.52. So copper reduction, that's the wrong copper. That's copper 1 plus. That's copper 2 plus. Here it is, copper 2 plus, 0.34. So the reduction potential for copper 2 plus to copper metal is 0.34 volts. That's the standard potential for that reduction. If we compare that to zinc, let's see, where's the zinc? Zinc. There's zinc. Minus 0.76. Which one is more reactive? The one that's more reactive is the one that wants to lose electrons. So it's the more positive one. This one is more positive than that one. This is the more reactive metal, which means it wants to lose electrons. Oh, excuse me. No, I got that backwards. This one is the more reactive one. this one wants to oxidize. So the more reactive one is the more negative one. Because these are all reduction potentials. In order for this one to be reactive, it would have to lose electrons. We would have to write it this way. And the voltage would be 0.76 volts. So the more negative the value as a reduction, the more active the metal. So it wants to go this way, wants to go that way. And if you compare them like that, right, this is the reaction for the left-hand side, the anode. This is the reaction for the right-hand side, the cathode. While we're here, when you put these two together, add them together, plus 0.75 and plus 3.4, you get 0 and 1.0 volts. That would be the theoretical maximum voltage, standard voltage for that cell that we wrote before. Now, your authors, your book says, you take the, when you've got these two cells together, you decide which one is the cathode and which one's the anode. Right? Well, if you're told which one's the cathode and which one's the anode, then it's simple. You just take the standard voltage for the cathode and subtract the anode. But we're subtracting the anode because we changed the sign. So I like it better if you put the two half reactions that are going to go together and you say, all right, if you change the sign of one of them, what does it do to the total? If we change this to a negative and add that to a negative, we get a negative sign. That won't work. This one cannot be the anode. It has to be the cathode. Then we change the sign for this one, we get a positive voltage. That's the one. That makes a whole lot more sense to me than just memorizing that formula. Now that's the standard reduction. That's the standard potential for the cell when you add those two together as cathode and anode. But that's not necessarily the voltage that you'll get from your cell unless you have 1 molar solution of zinc 2+ and 1 molar solution of copper 2+ here. That's the only way that you will get that voltage at 25 degrees. What you actually get depends on the true concentrations. And for that, we need a little more work. All right. So if we've got iron 3+ going to iron 2+, that would be a reduction. We've got copper going to 2+ copper, that's an oxidation. So we can tell which one is which in this case. Right? There are the half reactions. There's the iron at 0.77 reduction. Right? That's probably the way it should be written because we went from 3+ to 2+. Copper 2+ to copper is reversed. It needs to go from copper to 2+ copper. Right? So in order to do that, we flip the equation, change the sign, then add them together, and do we get a positive value? Yes, we do. So that means that the iron side of the reaction is the cathode, and the copper side is the anode. And the electrons are going to flow from the copper side to the iron side. All right. So there's the overall balanced equation. And in order to determine the true voltage of the cell, we need concentrations of the ions, right? concentrations of the metals won't change. Concentration of the ions will change. The concentrations, and we need to know the number of electrons that move. All right, so in this case, we've got a copper that loses 2 electrons and an iron that gains 2 electrons. So the total movement of electrons is 2 moles for this reaction. Right? And the cell potential, the standard cell potential is 0.43 volts. So we do need to know how many electrons are transferred in order to calculate the actual cell voltage. And we're going to do that by using the Nernst equation. I have to tell you what the Nernst equation is. And also, we need to know the stoichiometry. We need the balanced overall equation so that we can calculate Q, right? If you have an equation, a balanced equation, where you calculate K, what does that mean? K means equilibrium. If this system is at equilibrium, then nothing's moving. No electrons will move, right? Because the forward reaction and the reverse reaction are balanced. In order to have electrons moving and get a voltage, right, we have to be in a Q state, not at an equilibrium state. So we have to be able to calculate the Q based upon actual concentrations and the stoichiometry of the reaction. All right. So we're going to get to Nernst equation in just a few minutes. Let's see. I'll leave that up there for now, just in case we need it. So we're going to digress for a moment, and we're going to look at these species. The neutral iron, neutral sodium, the fluoride ion, the sodium ion, and fluorine. And we want to arrange them from strongest to weakest oxidizing agent. So what does that mean? If we're going from strongest to weakest oxidizing agent, that means your oxidizing agent has to be reduced. So which is the most likely to be reduced? Strongest, reduced, reducing potential, to the weakest, reducing potential. All right. The most easily reduced is the strongest oxidizing agent. So we need to order them by the largest positive standard reduction potential if possible. Okay, so here we go. We don't know the values for sodium metal, for fluorine, and for iron. We do know these values. We know the reduction potential for iron 3+. We know the reduction potential for chlorine. We know it for sodium ions, right? So that's good. And we know it for fluorine. Add 2 electrons and get fluoride ions. So how are we going to compare them as reductions? Right? What's their reducing potential? Right? So what's the voltage here? If we go from 1F minus to F2 minus. Or we go from sodium ions to sodium. Right? We know, let's go back. There we go. That's sodium going to sodium ions to sodium. Right? Is minus 2.71. That's an easy one. If we go from sodium to sodium ions, then we have to reverse that value. I would think it'd be a positive. If we go from chlorine there we go. There is a value for that one. The value for iron to iron 3 minus, we don't know. All right, so what could that one be? Well, we're looking at each one. What we're saying is that the hardest to reduce would be a metal, pure metal, right? Sodium. Be the hardest to reduce. So it's make the lousiest oxidizing agent. Chlorine would be the most easily reduced because its value is positive 1.36. That's the largest one of all the, well, yeah, because we don't have fluorine in there, right? Chlorine, it would be the most easily reduced out of that group. So iron is another metal that's not going to be easily reduced, but it's more easily reduced than sodium. And that sodium is more easily reduced than the iron, minus 271. And then the fluorine. Fluorine ion is already reduced. You're not going to add another electron to fluorine. So we're saying that fluorine would make the worst oxidizing agent. You cannot reduce it. And then the metals would be the next worst. And then the ion sodium would be reducible. And the chloride would be the most easily reduced. Right. So there's the explanation in black and white and red. Okay. So let's go. Yeah, I'm going to leave that up there. Let's say we had, let's go back to, let's see, we had the chloride ions coming out here. Let's change this back to where it was. A solid electrode of zinc. And then we have zinc 2+ ions here. And we're going this direction, right? That way, so that the electrons can move this way. All right. So there's a simplified version, a simplified notation for galvanic cells. And there are some conventions, of course, that we have to learn. These describe the this cell. This is be kind of messy to have to write one of these every time you wanted to describe a galvanic cell. So what we're going to do is we're going to use a convention, anodes on the left, cathodes on the right. Okay. So what happens in the anode? Well, of course, we're going to separate what happens with a double line. So if we put a double line here, that double line is either a salt bridge or a porous disk. It separates the two cells. On this side, we're going to have the cathode. On this side, we're going to have the anode description. Okay. The electron movement for this arrangement is from anode to cathode. Okay? So that means the electrodes have to be on the outer side, out here. So that means on this side, we're going to have copper. And on this side, we're going to have zinc. Okay? And it's advisable to also specify the phase. Because sometimes you won't have a solid electrode. Sometimes you'll have to use a platinum electrode or a carbon electrode, and the reaction occurs at the electrode, but with species that are in solution. Okay, a single vertical line anywhere in this arrangement signifies a difference in phase. So we've got a difference between solid and aqueous zinc. And this side, we've got solid and aqueous copper. Okay, that would be a very simplified line notation for our galvanic cell. And if we don't write anything else in here, we have to assume that this describes the standard cell with 1 molar concentrations, 25 degrees Celsius. And since there are no gases here, we don't have to specify pressure. Here's another example for this cell. The magnesium 2+ and the magnesium would be on this side. The aluminum and the aluminum 3+ would be on that side. And the electrons would move from the magnesium electrode to the aluminum electrode. There's the anode. There's the cathode. Okay. So, like I mentioned earlier, if you have a reaction where the electrode does not participate in the reaction, we'll use a conductive metal that's non-corrosive like platinum. Or in some cases, we'll use carbon because it's a lot cheaper. But it has to be chemically inert. I guess we're not going to give you an example right now, but there are examples. I'll call your attention to them when we get there. Okay. So this one tells us to describe completely the galvanic cell based on the following half reactions. Okay. If we've got silver plus electrons yields silver metal, that's a reduction, and the reduction potential is 0.80 volts. 0.80 volts. Right. And we have the other one, and we want to connect these together, but we don't know which way the electrons are moving. So we have another cell that's 3+ plus 1 electron yields 2+. Right? That's aqueous. This is aqueous. And its voltage is 0.77. How are we going to describe this? We have to decide which one is the cathode and which one's the anode. The cathode will stay reduction as written. The anode will flip and change the sign. So if we flip this one and make that negative, then the summation will be negative. So we're not going to flip this one. This one is going to be the cathode as written. This one is going to flip. To a negative 0.77 volts. Now, when we add them together, we get a positive 0.03 volts. Not much, right? That would be 30 millivolts. That wouldn't be very useful, I don't think. And that would be the overall reaction as written, with the standard potential. Okay, the electrons are going to flow from this side to that side. This is the anode now. Let's see, they want us to write the line notation for this one. That's what it would look like. Right, there's the cathode anode arrangement, this time with a porous disc. And notice that on the anode side, we have a platinum electrode. Because both of the species in here for the anode are in solution. So the reaction occurs at the surface of the platinum electrode because that's where the electrons are being lost. But the reactants are in solution. So the line notation then would be, let's say, anode on the left. So what we have is, right, there's our division of the cells. Let's do the right-hand side first. It'll be easier. We have the silver over here, right? Silver solid. Then we have silver in aqueous solution right there. On this side, we have division here has a platinum electrode. But in here, we have Fe2 plus and Fe3 plus. Now we know from the fact that this is the anode, which one is which, right? This one is going to that one and losing electrons. Let's see if I got it right. Well, it's aqueous. I'll let that part out. Aqueous. There we go. That would describe the cell. See, there's no phase difference between these two. That's why only a comma. Okay. This is just reminders. Right. So that would describe the complete galvanic cell. All right. This would be the this would be a different cell. This one where copper is in the anode and silver is in the cathode. And at 1 molar concentration for each, that's what it would look like. And our salt bridge has sodium nitrate in it. I don't know why I chose sodium nitrate, but yeah, I do. I know exactly why I chose sodium nitrate. What would happen if we had sodium chloride in there or potassium chloride? Once those chloride ions found their way into the silver cathode, they would start precipitating silver as silver chloride. And then it wouldn't be available for the reaction. You would have a competing reaction. So that's why I use sodium nitrate, because if nitrate ions migrate or find their way into the cathode, then they won't precipitate silver. All right. So what would happen to the potential of the cell if you increase the copper 2 plus concentration? The anode reaction is copper yields copper 2 plus 2 electrons. All right. So let's see. Let's erase this and erase this. And let's replace this with the copper electrode. Okay, so we're going to have copper solid yields copper 2 plus 2 electrons. And let's see, 0.34 minus 0.34, which would be a total voltage, standard potential, excuse me. Standard potential for the cell would then be 46, 0.46 volts. Okay. if we balance the equation, we need 2 electrons here, 2 there, 2 there, and 2 here. All right, so if we combine these equations, then we have 2 silver plus copper yields 2 silver metal plus copper 2 plus. So this is our balanced equation. Okay. Now, what would happen if we increased this concentration? Increase the concentration of copper. Well, the force, now this cell is not at equilibrium, but we can still use a little bit of the Le Chatelier reasoning. If we increase this value, it's going to resist movement in that direction, right? So it's going to oppose the movement to that side because we've increased that concentration. So the voltage should decrease. That should decrease the cell potential. Let's see. Mathematically, reduction potential will increase and reduce the magnitude of E plus for the cell. Okay. I like Le Chatelier reasoning better. We mentioned earlier what voltage means. 1 volt equals 1 joule per coulomb of charge moved. So that means at this voltage and with a certain number of coulombs of charge moving, we can get that much work out of it. Now, the problem is when we talked about work, remember the system versus surrounding scenario. If something leaves the system, it's negative. Right? So if we have, if the system is doing work on the surroundings, then this work is negative. But if it's a spontaneous movement, then the voltage would be positive. And so there we have a discrepancy in sign. They have opposite signs. So what we end up with is, in reality, when we write this as a solvable equation, this is an equivalence, 1 joule per 1 coulomb. But when we write it as a solvable equation, then we have the work component needs to be changed negative sign so we get a positive voltage, right? Because this has to be positive in order for this to be spontaneous. And then Q is our abbreviation for charge. Right? I know when we were talking about calorimetry, Q was heat, but in this case, Q is charge. So if we solve for work, right, negative W equals the potential times the charge. Okay. And the maximum work, if we just substitute max in here, the maximum work is the maximum voltage, the maximum potential for the cell times the amount of charge moved. All right. So there we insert, I just inserted the values here. This is voltage, this is joules, and this is coulombs. All right. So in any real spontaneous process, some energy is always wasted, right? We learned that when we were talking about thermodynamics. No matter what you do, you're going to lose some energy. Either, well, obviously, you're going to lose some of it to entropy. Right? That's unavoidable. But the actual work you get from a process is always less than the calculated maximum. But we have to know where the maximum is. Otherwise, we won't have a relative position to know what less than is. All right. So I mentioned converting coulombs to moles of electrons. And in order to do that, we need this value, which is identified as the Faraday. And that is named in honor of an English scientist who did phenomenal work on electricity in the 19th century. Faraday. So if we want to make a conversion, if we know the coulombs and we want to find out how many moles of electrons, we need the Faraday, which is 96,485. 1 Faraday equals 96,485 coulombs for every 1 mole of electrons. Okay, that's our conversion factor, right? And it'll be in useful information, so you don't have to memorize it. Just use it a lot and you'll have it memorized. All right. So if we go back to the previous chapter, 17, excuse me, 17. The maximum work that can be obtained from any process, thermodynamically speaking, is equal to free energy, change in free energy. So I think I need to make some room now. And let's see. Let's remove this and this. Yeah, I'll keep this other stuff just in case. So we're saying that the maximum amount of work is equal to change in free energy. And remember, change in free energy, to be spontaneous, must be negative. Right? So the maximum amount of work is equal to this minus Q. Let's see. Oh, we're going to move the sign. Move the sign over here. Right? Minus Q times E max. And that's equal to delta G. Let's write it up here. This is equal to negative potential, maximum voltage, times the charge moved is equal to delta G. And that's also maximum amount of work. There you go. Now, what's Q? Well, Q is in coulombs. This is in coulombs. Right? So, if we want to relate this physical property to chemistry, we've got to gain access to the number of electrons moved. Then we can introduce it into our stoichiometry. Right? So why is Q equals NF? Well, this is N, the number of moles of electrons, and this is Q charge. So Q equals the number of moles of electrons times the Faraday constant. All right, that's where that came from. Now we can substitute NF in place of Q right here. Substitute that one in here. Right, so that will give us delta G equals negative NF. Keep the negative, and then we'll move this one over here, right? NF times the maximum voltage for the cell. So delta G is equal to this relationship right here. Oh, there's Michael Faraday. He was a relatively young man when he did a lot of his work, which is not unusual in the sciences. But Michael Faraday was a self-taught scientist. He didn't have a doctorate degree from some university. He was just very attentive. He read voraciously, and he had a mind for experimentation. He would devise experiments that were very simple, but answered numerous questions. In sciences, we call that elegant. Okay. So this maximum potential is directly related to the free energy between reactants and products in a cell. So if we can calculate the difference in free energy between reactants and products, we can get a handle on maximum cell potential also. Right. So these are going to be under standard conditions. All right. We also know that the spontaneous direction is a positive cell potential. And it's also a negative delta G value. So those two will designate a spontaneous reaction. Right? So if this is positive, that will be negative. All right. Now we're going to switch gears just a little bit. I'm going to let that drawing do the talking for us, rather than draw it all up here on the board. Remember, when I said, if your reaction is at equilibrium and we have a K value, then there's no movement of electrons, right? K means dead battery. K means equilibrium. If you're at equilibrium, there's no cell potential. But if you've got a Q value, if you have Q is equal to some value, then your cell will have a positive voltage in one direction or the other, whichever is spontaneous. Well, we're going to take that idea and actually create a galvanic cell with the same half reaction in both cells. Now, how do we do that? We create a situation where one cell is more concentrated than the other one. In this case, and this is the case for any two half cells, the cathode will be the higher concentration, the anode will be the lower concentration. And I hope this explanation will clarify. All right, we have different concentrations in our half cells. And Le Chatelier says that the lower concentration will increase and the higher concentration will decrease. Now, if we write those half cells like, let's see, we got silver. Okay, so the cathode side is going to be silver plus an electron yields silver metal. And I'm going to designate this as cathode. Cathode. Okay. The anode side uses the same reaction, but it's the other direction. This is the anode side. And it's going to be, let's see, silver plus anode plus an electron. Okay. Now, if we pull these two together, then, let's see, let's put the anode over here. Silver, solid, anode, plus silver plus cathode. And then we're gonna put, let's see, silver plus anode plus silver solid cathode. Okay, so I'm gonna underline the cathodes here, just so it's easier to see. All right. So if these concentrations were exactly the same, what would happen? Nothing, right? There's no push on those electrons if the concentrations are the same on both sides. But where are the electrons moving? Right, let's see. The electrons are moving. Let's see. We've got electrons coming in from this side from the cathode. Excuse me, from the anode. And they're coming out this side from the cathode. Right? Because we're making metal here. If we unbalance this arrangement, say if we increase the concentration of the cathode here, if we increase this one and we decrease this one, right? The anode side, decrease the silver concentration, increase the silver concentration on the cathode side, then which way is the reaction going to go? You increase this one, it's going to go to the right and produce a positive voltage. This is what's known as a concentration cell. This side, the anode side is going to have to increase the silver ions. In other words, as we add, if we increase this one over that one, then the reaction is going to push to this side and increase the concentration of silver ions on the anode side. And the only way it can do that is to take silver from the electrode into solution. That will give us a voltage, a positive voltage. All right. Now we're going to look at how do we calculate the true voltage of a cell based upon concentrations. And that's where Walter Nernst comes in. Let's see, what can we say about Nernst? In those days, right, in the latter part of the 19th century, early 20th century, thermodynamics was big because we were getting into the use of steam power, right? We're getting away from animals, now we're moving to machines. And understanding steam power and how to make it more efficient was a driving force for much of the research. Well, he wasn't just involved in thermodynamics. Of course, he dabbled in other things, and electrochemistry was one of them. So he came up with a concept and an equation that would help us solve our electrochemistry problem. And it also, the work in thermodynamics got him a Nobel Prize. The Nernst equation he developed in the latter part of the 19th century. Let's see. Yeah, well, we were introduced to that one in the last chapter, so I'm not going to beat that horse. Okay. So here is the Nernst equation in its fundamental form. if you want to know the true electrical potential for a galvanic cell, you first need to know the standard potential. And then you modify that value with these terms. The gas constant, right, with the energy term, 8.3145 joules per mole K. The temperature in K, the moles of electrons. N is the number of moles of electrons that moved in this reaction, and the Faraday constant. And then you multiply that times the natural log of Q. So you have to be able to calculate Q for the reaction based upon the balanced equation, overall equation, and the concentrations of the components. Now, since natural log is a little difficult to work with, and temperatures are usually standard, 25 degrees, and the Faraday is a constant, then, and R is a constant, then we can modify this equation so that it's a little more user-friendly. And that's what I've done here. I've shown you the procedure, the calculations there in that blue box. And what we end up with is this modified Nernst equation at 0.0591 divided by the number of moles of electrons and the common log of Q. Okay, this is the one that we're going to be using. Now, if you use a different temperature, right, then you need to go back to the original. But for our purposes, we're going to stick with 25 degrees Celsius. And this little box on the right is just to prove to you that this factor that I used for modifying the natural log to the common log is valid, right? But you don't have to memorize that or anything. It's just proof. Okay. So at 25 degrees Celsius and equilibrium, Q equals K and E equals 0, right? I mentioned that earlier. But the value of that understanding is if our cell is at equilibrium, that means this value is 0. But this value is still under standard conditions. That's right. So we keep this one. Right? But instead of Q now, we have log K. Because we're at equilibrium, that value is 0. So if we're at equilibrium and we know this value, then we can calculate K for that reaction. We know that we can calculate the equilibrium constant. Okay. Let's see. For this oxidation reduction reaction, we have voltages, standard reduction potentials, balance the redox reaction and calculate E0 and K. All right. So I think I'm going to do that on the next slide. All right. We have to balance the number of electrons first. We have to decide which one is anode and which one's cathode. So we determined that we had to reverse the sign, right, on the anode. And in order to balance the equation, now we will have to multiply the anode times 2. Right, so when we add those together, that's the balanced equation. There's the E0. Now, calculate for every 2 moles of chromium 2+ reacted, you get 2 moles of chromium 3+ and 2 moles of thiosulfate ion. N equals 2. That's important. We need to know that value right there. How many electrons moved? Actually, 2 moles of electrons. So now that we can substitute, we solved for log K. Right? log K then is equal to, let's see, move E over here and then N times E0 divided by 0.0591. That should be. Yeah. So if we substitute the values in here, we determined that 0.67 volts was standard potential, 2 moles. That's the log K, and then we take the anti-log of that value, and we get K equal to, hold on a second. There we go. K is equal to 4 times 10 to the 22nd. That's a huge, huge value for K, which makes sense. If the cell is moving in a spontaneous direction, the K is going to be a large number. It's going to prefer the product side. All right, what's the difference between E? When is E equal to 0? That's when the cell's at equilibrium, dead battery. When is E0 equal to 0? That's when both the anode and the cathode are exactly the same reactions at the same concentrations. Well, actually, E0 is the same no matter what the concentrations are, because it's under standard conditions. All right. So let's say for this, let's see. Erase this part. I'm going to leave that part just in case. And do that. We don't need this. A concentration cell is constructed. Let me see how much more time I have. Okay. I think we can finish. What's the potential of this cell? All right, if we're using a concentration cell with nickel 2+ and nickel metal, then the cathode is going to reduce the nickel and the anode is going to oxidize the nickel metal. If we combine the two, then we get this reaction that I've shown in the combined here. Okay. Now, combining the two, we get the log of Q. So what's Q? Well, we can't use the solids. Remember, when you calculate K, solids don't count. So the concentration of 2+ in the anode divided by 2+ in the cathode is the term by which we take the log. And then if we know that we have 2 electrons moving, we can substitute 2 in for N. E0 is going to be 0, right? Because this is a concentration cell. And we can calculate the electrical voltage. In this case, with those concentration differences, we should get a voltage, a maximum voltage of 0.118 volts or 118 millivolts. All right. So let's say you have a galvanic cell at 25 degrees, nickel electrode in 1 molar, nickel 2+ should give you a reduction potential of minus 0.23. Silver electrode will be plus 0.8 under standard conditions. All right, what's the question? Oh, sketch the cell, label the anode, cathode, showing the direction of electron flow, and calculate cell potential. Cell potential is easy, right? If we turn the silver electrode into the anode, it will make a negative plus a negative, which is negative. So the silver has to be the cathode. It's the reduction side. So the nickel is the one that we reverse. And the total then would be 1.03. That's easy. Right, that's the standard potential. And there's the line notation. right? That's what it would look like. We put the cathode on the right with the silver and the anode at the left with the nickel. And there I am again using nitrate, right? Because silver nitrate is soluble. We don't want any chloride in there. All right, so there's our standard potential. And now we're going to talk about other types of galvanic cells first. Then we're going to talk about what happens when you run the thing in reverse. And this is a good place to start because everybody's got a lead acid battery in their car. And you use up some of that stored electrical energy in that battery to start the engine and to run accessories. And the only way that you can replace that energy is to run that cell in reverse, right? You create a higher voltage to run in opposition to the spontaneous direction, and that recharges the battery. It runs the reaction in reverse. Now, the nice thing about the lead acid battery is you don't have to separate the cells. Well, the plates, the electrodes have to be separate, but the solution in which they're submerged is the same for both because of the reaction that's undergone at each electrode. So there's the overall reaction. And notice that sulfuric acid is essential. But each one, both the lead and the lead oxide, end up as the same product. So that means that your solution doesn't require a salt bridge or a barrier of any kind, right? The same solution is the solution into which both electrodes are submerged. No need for a salt bridge. So if the battery is completely discharged, both electrodes are converted into lead 2 sulfate, which is a solid, right? The solid deposited on the electrodes. So in order to run the reaction in reverse, you've got to be able to have access. The solution must have access to the electrode underneath. And when we run the battery in reverse, we call it an electrolytic cell. Okay, I'll say one more thing about this. Sometimes with multiple charge, recharge, discharge, and charge cycles in a lead acid battery, as you discharge it, you deposit lead 2 sulfate on the electrodes. When you recharge it, you're converting that lead sulfate on one electrode back to lead and on the other electrode back to lead oxide. The conversion is not 100%. You always leave a little bit of lead sulfate behind. And with every charge cycle, you add more and more and more lead sulfate. So over time, the surface of your electrode is coated with the solid lead 2 sulfate. And that means that the solution no longer has access to the electrode underneath, right? And to the reactants underneath. So when that happens, you may not have used up all of your electrodes, the lead electrode and the lead oxide electrode, but your battery is still dead because it does not have access to the electrode underneath. At that point, we say that the battery is sulfated out. In other words, you might as well recycle it. Okay, here are other types of dry cell batteries. This is like the D-cell battery that you can get buying at Walmart. The anode is the zinc casing. And of course, it has a plastic covering on the outside. And then the reaction takes place in that paste. So we call it a dry cell because if you punch a hole in it, it doesn't immediately just run out. Right? But it's not complete. It's more like a gel than it is a liquid. Now, the cathode is this carbon rod, which does not participate in the reaction. The reaction occurs at the electrodes, but in the paste. All right. Here's another type. This one is one that's not used much anymore because it has mercury in it. But it's the type of structure, the type of cell that you would find in calculators, hearing aids, small devices. We've got another chemistry that's substituted now for the mercury that looks the same, but it is not as hazardous. This is a type of battery called a hydrogen fuel cell. And it's the holy grail of a sustainable energy economy. If we can find a cheap source of energy to split water, electrolyze water, and produce hydrogen gas and oxygen gas, right? The spontaneous direction is this way. So we need to put energy in to make it go that way. In this case, we would need, let's see. We need 2 here, 2 here. Once you've got this hydrogen, and there's plenty of oxygen in the atmosphere, you can run the hydrogen through your fuel cell, and the anode is where the hydrogen is oxidized, and the cathode is where oxygen from the atmosphere is brought in and it's reduced. And you get this external flow of electrons. Now, the technology is much more complicated than this. Some cells run at low temperature, at relatively low temperatures, and some run at very high temperatures. So that's an engineering problem. Now let's talk about corrosion. What do we mean by corrosion? Most metals on the Earth's surface, in the crust, anywhere that we can access them easily, are combined with other elements. In other words, they've already been oxidized. So in order to make them useful, we have to process them, we have to smelt them, which is a process of reduction. We reduce the metal to its metallic form. We add electrons to it and convert the ion to metal. Well, those metals are very reactive, some more than others, when they're exposed to an oxygen atmosphere and a little water. And what you get is a reversion of that metal to the oxide in most cases, sometimes to the sulfide. But the process is called corrosion. You're oxidizing the metal. If it's iron, you get rust. And this is a diagrammatic explanation of what happens to the surface of iron when a water droplet hits it, sits there. Right? It sets up a galvanic cell with the anodic area down here where you're producing iron 3 oxide. And over here, well, this is the rust, it builds up over here. And the cathodic side where oxygen is being reduced. You're making water. That's corrosion. Now, there are ways to prevent corrosion, right? One way is just to put a coating on the metal so that the air can't get to it. You can do that with paints, which has to be periodically refreshed. You can coat it with another metal that is more reactive, like zinc. That would be galvanizing. Right? We used to have galvanized buckets all over the place. Steel buckets that have been dipped in liquid zinc. And they'd have a nice, pretty crystalline pattern on the surface. But that would protect the steel underneath by oxidizing the zinc instead of the iron. You can alloy. You can combine iron, for instance, with chromium. And originally, it was about 13% by mass. Would produce stainless steel. What that would do was, if there were any damage to the surface, say a scratch on the surface of your stainless, the chromium would instantly react with oxygen and seal the surface so that no air could get to the underlying iron atoms. Other alloys are also useful, like brass, right? If you alloy copper and nickel, you get brass, and brass is resistant to corrosion. That's why it's used on ocean-going vessels. There's another way, cathodic protection. This was used in the past when you had steel tanks underground, usually fuel tanks, or water tanks for that matter. These steel tanks would corrode over time. So what you would do is you would attach by means of an electrical cable to another metal and bury it in the ground near the tank. And that metal would corrode as the anode and produce an electron stream through the cable to the iron tank or the steel tank, and would continuously reduce the iron, keep the iron in a reducing state so that it would not be oxidized. And that sacrificial electrode here, the magnesium in this case, would preserve that pipe. All right. I just thought of another one. A cheaper way to make an alloy that's resistant to corrosion is to combine steel or iron with aluminum. So aluminized iron is often used in automobile exhaust systems because the aluminum will corrode faster than the iron and seal it so that the iron won't corrode any further. That's the reason that when you drink a can of soda in an aluminum can, if you throw it out 100 years from now, it'll still be there because the aluminum corrodes so fast that it forms a protective sheet of aluminum oxide on its surface, and no further corrosion takes place. All right. Cathode is the pipe, right? That's where the reduction is occurring. Okay. All right. If we want to run a cell in reverse, why would you want to do that? Well, one way, if you have the hydrogen fuel cell, that's spontaneously reacting with oxygen to produce electricity. That's a galvanic cell. If you run it in reverse, you're taking water and you're splitting the hydrogen and oxygen to separate from each other. You're running that cell in reverse. So that would be an electrolytic cell when you're producing hydrogen and oxygen from water. But you can do that with any battery or any galvanic cell. You can run it in reverse. And we run it in reverse oftentimes when we want to plate out a particular metal on the surface of another electrode. Right? So there's the example I mentioned for electrolysis of water. And in fact, this reaction occurs in your lead acid battery if it's overcharged, right? If the battery is fully charged and you're still pumping electrons into it, it's likely that they will split water molecules and produce hydrogen gas. And if hydrogen gas builds up in your battery, kablooey, right? Big boom. So, but we have electronic systems now that regulate the amount of electricity going in, and they shut down the flow of electricity when your battery is fully charged. But in the olden days, so to speak, batteries had vents on them. Their cells had vents, so that if the system overcharged the battery, then the hydrogen would escape through the vent and not accumulate. All right. So during electrolysis, there's a stoichiometry involved. And in order to know the stoichiometry, you need to know the galvanic cell that you're running in reverse so that you can follow the progress of the movement of charge converted to the movement of electrons, converted to the stoichiometry of the metal reduction. That's what this flow chart is all about. It'll make more sense when we do an example. All right, so if you're going to run a galvanic cell in reverse and make an electrolytic cell, then here's an example. You have an unknown metal that is electrolyzed. So we're going from the metal to, we're going from the ion to the metallic. And we're starting with, oops, that one's running out. Let's try this one. There's your metal, and it's combined with nitrate. Let's see, is it 2? No, it's 3, excuse me. 3. Nitrate is a spectator. So really what you got is the 3+ ion of the metal plus 3 electrons yields the metal. That's the stoichiometry. All right. So let's see. The question is, what's the metal? We want to identify the metal. So remember how we identified the metal in the past? If we know the molar mass of the metal, then we can identify it. So we need the mass of the metal, we need the moles of the metal. So what it's telling us is we're given in the product 0.0719 grams of metal are plated out. So we got grams per mole, 0.0719 grams. What we need to know is the moles of the metal. All right. When we plate it out, we have a stoichiometry here between the number of electrons and the moles of electrons and the moles of the metal. So if we can find out how many moles of electrons it was required to do that, then we can find out how many moles of the metal there are, and we can calculate the molar mass. So if we're going to run this current, 52.8 seconds. 52.8 seconds. And we're going to run it at 2 amps. 2 amps means 2 coulombs per second. That's what an amp means, coulomb per second. This gives us what? How many coulombs charge? 52.8 times 2. So we have 105.6 coulombs. Now we want to convert that to moles of electrons. So what's the ratio here? Moles of electrons. Actually, 1 mole of electron is, let's see, 90. Let me do my animation. Maybe give me the value, because I don't have it memorized either. 96,485. 96,485 coulombs per mole. So we divide this into that, and that gives us the moles of electrons. .09 times 10 to the minus 3 moles of electrons. How many moles of metal does that equal to? Well, it takes 3 of these to make 1 of those. Right? So 3 moles of electrons is 1 mole of metal. So we divide 3 into that. And we get 3.65 times 10 to the minus 4 moles of metal. Now we've got something we can put in here. Okay, 0.0719. It's 197 grams per mole. So we look that up, and that turns out to be gold. Our metal is gold. Okay. Let's see. Let's erase that one. Oh, it's gonna be stubborn. Use that marker anymore. All right. So we've got a solution containing 0.1 molar of each of the following: lead 2 plus, copper 2 plus, tin, nickel, zinc. Predict the order in which the metals will plate out as the voltage is turned up from 0. First question to ask yourself, if they're going to plate out, where do they occur? They're going to plate out on the cathode, right? Because that's where the ions are being reduced into metal. So the reduction potentials will predict the order of plating. The more positive the standard potential will plate first as the voltage is increased. Let's see. That's because it takes a higher voltage to compensate for a negative reduction potential. In other words, the lower voltage, if the voltages are positive, let's just put them up here. Do we have, I got a list here. Yeah, okay, I got a list. There we go. And one more. One more. Okay, look at it this way. If we're going to drive the reaction to plate out metals, the total potential must be positive. So if we're running the voltage backwards, the only way we're going to get a positive potential is for the voltage to exceed the value of the reduction. And it exceeds the value of the reduction and gives us a positive voltage only, well, first, if the reduction potential is positive. So 0.16 is going to go first, copper. And then the next, the smallest negative would be lead, and then tin, and then nickel, and then zinc will go last because it is the most negative. That's the order that you will plate out. Okay. Electrolysis of various ores is one way to produce the metal. Now, chemical reactions for some metals like iron, you can smelt them with pure chemistry, right? And just the right reactants and enough heat, and you get the reaction. But for aluminum, which is an extremely reactive metal, we have difficulty chemically, purely chemically, producing aluminum metal. That was the way it was first produced and first discovered. But there was a time when it was so expensive to produce aluminum that way that it was worth more than gold. And the story is told that the King of France, Louis XIV, I think, would serve, rather than gold utensils, he would serve aluminum utensils to his guests to impress them, because everybody knew just how expensive aluminum was. The price of aluminum now is dropped so low that we can make foil wrap out of it, cook with it, and throw it away. And that was made possible by engineering in such a way that we could electrolyze aluminum oxide, bauxite ore, and produce aluminum metal. All right. So this is actually there were two people working on this process simultaneously. One's name was Hall and the other one was Hérault. He was French and Hall was American. And they came up with essentially the same system. So we hyphenate the name and just call it that. But what's done is, in order for electrons to move, the solution has to be molten. In other words, you got to be able to move your ions to the electrodes. And you can't do that if you're using solid aluminum oxide. So what Hall decided to do was combine aluminum oxide with some other material that would lower its melting point. That way it didn't take as much heat to get the aluminum oxide in a molten state. And then at the cathode, he would drive an electric current into the solution, and that would plate, that would cause aluminum to be reduced to the aluminum metal. And actually, rather than attach itself to the carbon, which it rejected, it would just settle to the bottom. And then you just tap the plug and you get your molten aluminum out. Now, the carbon electrodes were eventually depleted in such a way that you would have to replace them too. But that initial change reduced the melting point from over 2,000 degrees to just under 1,000 degrees, which was a considerable amount. And that, what you need is a ready, cheap source of electricity. That's why Alcoa located its processing plants either near hydroelectric sources or near rich coal fired power plants, like Pennsylvania, for instance, or the Tennessee Valley. You need cheap electricity to do this. In this case, we can electroplate spoons. All right, we turn the spoon into the cathode, and we drive a current through it so that we can take silver from the other pure silver electrode and deposit it on the cathode. This is basically a concentration cell run in reverse. We can also produce pure sodium and pure chlorine gas. We electrolyze sodium chloride. And then you can take the chlorine gas and do lots of things with it. You can make bleach, right? Just bubble the chlorine gas through sodium hydroxide solution and make bleach, sodium hypochlorite. And you can take the sodium metal, and I guess you can do a bunch of stuff with that. I just don't have any idea off the top of my head what. Okay, that's it. We're done with chapter 18, and now you'll have to review the problem set that I gave you in class, and which is available in Brightspace. Review that problem set with the video that's also in Brightspace, so that you'll be ready for the exam on this material next Monday during the final exam week.